Hello, hey there, welcome. Yes, let's continue with our problem. This time, we're moving on to state 11, state 1 to be precise, correction. So, we're moving on to state 1, state 11 is all done. Moving on to 1. All right. So at step 1, what's happening at step 1? Observation is that TS diagram tells us that we are at the saturated liquid. So we just read HF is equals to H1. We're done with step 1. Then we move to step 2. So step 1 would be HF at state 11. So we do need to do some interpolation here to get HF. So use this space here, I'll say state 1 pressure at 1 is equals to 11 kPa, and I'm just gonna read HF11, which is the same thing as H1. So 11 minus 10 divided by 15 minus 10, that gives me 0.2. Okay, therefore HF1 is equal to 0.2 multiplied by 225.94 minus 191.81 plus 191.81. That gives us 198.64 kilojoules per kilogram. So that's the value for H1. 198.64. We're done with state 1. State 1 is done just like that. Okay, maybe we do need to get V1 also. 0.2 multiplied by where's that? Multiplied by 0.00114 minus 0.001010 plus 0.001010. That gives us 0.00101008 meter cube per kilogram. All right. That is V1. Now we can officially say state 1 is done. Let's move on to state 2. What do you know about state 2? Well, to understand state 2, let's look at the test. Okay, let's look at the schematic diagram. From state 1, work is done to the fluid or the working fluid, which is a saturated liquid. Work is done by a pump to raise the pressure to state 2. Okay, therefore we can use this in our formula to get H2. We could say H2 is equal to the enthalpy at state 1 plus, what is the formula for work done? The formula for work done of a pump is equal to the volume, assuming that you cannot compress liquid, cannot compress water, constant volume multiplied by change in temperature P2 minus P1. That is work, so that is the formula we are going to use. V1 should be equals to V2 multiplied by P2 minus P1. And what is P2? TS diagram tells us that P2 is the pressure in the open feed water heater, which is 0.7. So that's how this one is done. So getting the properties at step 2 is a straightforward process. So I would say at 2, which is the same thing as step 2, we would say H2 is equal to, what is H1? 198.64 plus 0.001008 multiplied by P2. What is P2? 0.7 times 10 to the power 3 minus 11 kPa, multiplying by 10 to the power 3, thus converting the 0.7 megapascal to kPa, and that should give us 199.33 kilojoules per kilogram. Just confirm this on your side, please. All right. What's next? Move on to step 3. What happens at step 3? At step 3, we have the liquid leaving the open feed water heater. And what we know about the open feed water heater is that everything that goes in the open feed water heater mixes, comes in contact, and then it leaves as saturated liquid in this case. So that is a saturated liquid, and what we have right there at step 3, that is saturated liquid. At what pressure? At the open feed water heater pressure. So we got 0.7 megapascal, and we read HF. So that is at 700 megapascal, and we'll read HF. So 700 megapascal, and we read HF. HF is 697. There it is. So at step 3, at a pressure 0.7 megapascal, 700 kPa, at HF3, which is equals to H3, we just go and read off the table, and H3 is the same as HF at a pressure of 700 kPa, and that is 697. Okay, that is HF. What do we know? There's a pump immediately after H3. So from step 3, the pressure is raised to the boiler pressure by a pump. So we can actually get the properties for step 4 using the work done the working fluid by the pump. So at state 4, this is what I mean. There's a pump from state 3 to state 4. There's a pump. So we have a pump from state 3 all the way to state 4. So the pressure is raised by a pump. Therefore, we can use that in our equation. So at state 4, what is the pressure? It's the boiler pressure of 10 megapascal. So I would say enthalpy at state 4 is equal to enthalpy at state 3 plus V3, need to get V3 plus P4 minus P3. Okay, we have H3. What is H3? 697.0 plus, did we get V3? Nope. Let's get V3 goes to VF3. That is VF3. Okay. 0.001108. 0.001108 meg. What am I saying? Excuse me. Meter cubes per kilogram. Multiplied by what is P4, 10 megapascal times 10 to the power 3 minus 0.7 times 10 to the power 3. This should give us H4 of 707.30 kilojoules per kilogram. Confirm on your side, please. Alright, that is state 4. So those are the properties at state 4. Alright, what's next? You can pick any state, remember. Okay? Move from H4, can move to H5. Okay. H4, now move to H5. Now, the thing about H5 is we can't work out H5 yet. The textbook that I'm using doesn't tell us how to do that, but that's fine. There is a way to do it, of which I will not go into details now. For now, we'll leave state 5 alone and move on to state 6, get H6, and once we get H6, so we'll leave H5 alone, we'll get H6. Once we get H6, because the question tells us that the feed water is heated to the condensation temperature of the extracted steam in the closed feed water heater. That simply tells me that as feed water enters this closed feed water heater, it is heated to the temperature of the extracted steam. So in other words, I can assume that the feed water heater is living at the same temperature as that of our extracted steam at H6, which is the condensation temperature. So the condensation temperature or the saturation temperature, the condensation temperature of the extracted steam, that simply means, what is this? The extracted steam leaves the closed feed water heater as a saturated liquid. So if it leaves as a saturated liquid, I'll just go and just read off H6 as HF at a pressure of 1.3 megapascal, and the saturation temperature at 1.3 megapascal will be the same temperature for H5. I'll show you what I mean. On our TS diagram, H6 is exactly on the saturated liquid line. Why? Because the extracted steam leaves as saturated liquid. That's why. So at 1.3 megapascal, we'll go rid of is that right. We need to get that one. One 1300.3. So let's find all right. So there's HF. At 1.3. Oops. So yeah, at 1.3, the temperature is 191.6. So that is the same temperature for state 5. But for now we're at state 6, so we just go rid of HF, which is 814.59. 814.59. So we are at state 6 now. Pressure at state 6 is 1.3 megapascal, which is the same thing as 1300 kPa. So we just go rid of H6 is equals to HF at a pressure of at P6, which is equal to at 14.59 kilojoules per kilogram. Okay, cool. Yeah, that's all we need for now. And what do we know about H7? We know that this is a throttle valve and H6 is equals to H7. Therefore, if we have H6, we automatically have enthalpy at state 7, which is just H6 is equals to H7 at 14.59 kilojoules per kilogram. There we have it. We have step 7. Now at step 5, as it has been discussed already, that the feed water is heated up to the condensation temperature of the saturated steam. What that means is that T6, T saturation, is equal to T5, which is equals to, what is the temperature at T6? Saturation temperature. Saturation temperature is, where is it? 1300, 191.6. That is the saturation temperature. 191.6. All right. So at 191.6, I just go there and I read off my H5. 191.06 degrees Celsius. So I go rid of H5 equals to HF at T5, which is equals to T6. And that will be the same thing as H6, which is the same as H7 in this case, at 114.59. So that's how you get H5 for now. Simplified way to do it. So we have H5, we have H7, we have H8. All our states are defined now. Let me see. We have H1, we have H2, H3, H4, H5, H6, H7. We started with H8, we got H9, we got H10, we got H11. So all our states are now defined. So that's how you go about getting your enthalpy values and all your necessary properties to fix your state. So the only thing to say now is, continue learning, and God bless you and keep you. And please prepare for the exams and go and shine.